So here uh, it might happen that uh, it might happen that accessing of those six fields or those six attributes may be difficult to us. So that also we do not want to have. So if frequently I am accessing, executing that query, this may become costlier, and that's why here we are moving towards the solution where we are deciding whether given relation is in normalization form or whether given design is good or bad. So for this purpose, we are using this normalization. So initially we started with the lossy decomposition. Lossy decomposition, it means that if my design R is there, and if I divide R into R1 and R2, then whether that relation or that decomposition doesn't result into loss of some data. Okay, for this purpose we always use lossless decomposition. Lossless, it means that after decomposition, by applying some formulas, I should be or we should be able to get those relations properly or recover the previous relation properly. For this purpose, having a lossless decomposition is much more important. So anybody would like to ask any questions based on the last lecture?
Ma'am,
Yes.
can you brush up the all the content which are taught in previous lecture, within the 10 minutes?
Okay. Okay, I will brush up. So let us go through the all the content. So here the main point is that we are not taking point wise all the things. So only few slides we have covered previously. So we started with this chapter 4, relational database design, and these are the syllabus contents, features of good relational designs, and we just started with the second point, that is atomic domains and first normal form. Okay, so features of good relational design. So for this purpose, we have taken a schema where we combine instructor and department two relations together. So okay, for this purpose, I have taken example of department and instructor. So right now, department, this relation, okay, department relation, I'm having department name, okay, and I'm having a building in which the department is located, and budget. It means how much is budget allocated for the department. And in the instructor, we were having the fields instructor, ID of the instructor, name of the instructor, department name of the instructor, and salary. Okay, so these are the fields where previously we have taken. So, but thing here is that if consider we combine these two things together, it means if we combine the two schemas, then here instead of having these many fields, a combined schema, we will take this as a instructor department ID, name of the instructor, in which the department student or faculty is, and here salary I will take because salary is a personal attribute, that's why salary I will take here, and department name in which building the department is, and budget. Okay, so here these are the fields. This may be a combined schema. Okay, so here a combined schema, if we discuss about, if we take a single department, let us take a history department. In the history department, if there are 6 instructors are there, okay, if in the history 6 instructors are there along with the department name, these two contents will also go on repeating. It means the same information will be get repeated for the 6 instructors.
And that's why here I may say that this schema is a redundant schema or doesn't have a fixed structure or doesn't is not in the normalized structure. Okay, so if there is a redundancy of the data, we should divide or decompose the relation. The same example we have taken here. So physics, I have taken this instructor relation where 12 to 13 instructors are there. So physics Watson and 70,000, physics Watson 70,000. This data got repeated here. If I take a computer science department is located into Taylor building and is having a budget of 10 lakhs. Computer science Taylor 10 lakh, computer science Taylor 10 lakh. It means that whatever this information is there, which is based on the department name, that is getting repeated or that is getting duplicated or redundancy is much more added. Okay, so this may be having multiple problems. For example, consider right now whatever computer science department is there. Okay, so computer science department. So right now this is located into Taylor building. Okay, is it? Yes, it is located into Taylor building. But as per the update, it means later on because of some problem, we have shifted this department to some consider Watson building. Okay, so if consider we are distributing this for changing or for the single update, I need to update three tuples. Okay, there are three tuples of the computer science are there, and because of which I need to repeat this modifications at the three places. Okay, and that's why this, if redundancy of data goes on increasing, the problem or updations also gets increased. Okay, and consider another problem. uh, Consider that there is a department, a newly opened department is there, which I wanted to make entry just now. Consider production department is there. Okay, if production department is there, right now there is no any instructor allocated for this. And consider in the coming June or coming July, we are about to start this department. Right now there is a existence of the department is there officially, and the existence of physical existence is also there, that some building is allocated for this. Consider I will allocate Taylor building for this. So in that case, if there is no any single instructor is there, still we are unable to add this entry to the existing table. Okay, in this table, I'm having ID as a primary key. If right now just department is there, but there is no any faculty allocated for this department, so in that case, it becomes a difficult to uh, make this entry into existing table, and that's why this redundant schema may be having its own problem, which is called as an anomalies. Insert anomalies. Anomalies, it means problems. What problem we are facing with the insert. And next, if we are performing updations at more than one locations, this may called as update anomalies. Again, delete anomalies may be there. Consider that we have decided to remove any of the departments, and here consider that history department management decided to close. In that case, history, there is a instructor califrey, so he might be shifted to some another department, and ilsaid may be shifted to some another department. In that case, deciding or for deletion of this value, whatever the corrective steps are there, that may be also difficult, and for this purpose we also face problem in the deletion, which is called as a delete anomalies. Okay, so these are the problems which may be arise because of the bad design. Okay, so combined schema, here repetition of the work or redundancy of the work is also there, and updates problems are also there. And without repetition also, if consider that we are having only unique structure, for example here instructor is there, whatever current instructor table is there, we decided into two parts, that ID and department name should be in the one relation. That if consider that we decided to maintain only official information, ID and department into one relation, and ID name and salary. Okay, this information we are maintaining separately. Then dividing the schema into or decomposing this relation into a number of relations may be also harmful. That even though we do not lose the data, but access of data becomes difficult. For this purpose, always we should have a relation with the minimum redundancy and the ease of access. Okay, so this was the part. So here consider combining the schema. So wherever there is no repetition, in that case we can combine the schemas. So if even though we are having the smaller schemas, so smaller schemas, uh, maybe if we are having ease of access of the data, then we can divide this. And here, if we don't want, we are having lengthier schemas, then decomposition should be always lossless decomposition. So here we have seen this example that initially we are having the employee relation. In the employee, we are having ID of the instructor, name of the instructor, street, city, and salary. And consider that for decomposition, we have chosen the attribute common to be a name. Then ID and name parted into one relation, and remaining attributes name, street, city, and salary are parted into some another relation. Then here there is a repetition of the key value is there. And because of this, whenever we wanted to retrieve the existing first relation, consider that this is employee 1 and this is employee 2. So in this case, if consider we are having or we wanted to recover this relation, in that case, we may perform the natural join as a last option for combining. And as there is a common field name is there, because of which this scheme and this scheme are equivalent, and that's why in the final result we will get this as a data set into the relation, which gives a false data. That's why this type of the decomposition is called as a lossy decomposition, where we are not able to recover the existing complete relation. Okay, so this was the lossy decomposition, whereas we may go for the lossless decomposition if consider whatever the structure is there, instead of decomposing on the name relation, if we decompose ID and name as a one relation and ID, street, city, and salary as another relation, this may give us the existing correct relation. Okay. So then next, this example we have seen how to combine the relations. Then we move towards the first normal form, that domain must be atomic. So atomic, it means that if whatever our attributes are there, these should not be composite in nature. Whatever attributes we are listing into the relation, all these should be atomic in nature, and they should have an atomic domain which cannot be divided further. For example, if we take a ID of the student, then that ID cannot be divided further. Whereas if we take a name can be decomposed into first name, middle name, and last name. And that's why here name I would like to say as this is a composite attribute, and whereas ID etc. these will be the or Aadhaar number, phone number. These all are atomic in nature, which we cannot divide further. So we can say a relation is in first normal form if its all attributes are atomic in nature. Okay, if all the attributes of the relation are atomic in nature, then we can say that the given relation is in the first normal form. Okay, a relation schema R is in the first normal form if the domains of all attributes of R are atomic in nature. So non-atomic values complicate the storage, yes, and encourage redundant repeated storage of a data. Okay, so redundant, for example, let us take an example of the name. So name, there is no any fixed strategy that we should have first name, middle name, and last name only. So it might happen that I may store my name as Kadam Sanjuni Sachin, or this may be one way, or I may store the name as Sanjuni Sachin Kadam. Okay, so this here we are unable to identify whether this value and this value are equal or not. Yes, logically, whatever as a human, I can identify that these two values are same. But whenever we are comparing with the database, it will check by alphabet. It means database cannot identify whether this is middle name or this is last name or first name, etc. In that case, this value is treated as a separate or different value than this value. And that's why here we may go for storing these two records differently. Even these two records refer to a same person. Okay, and that's why here we are avoiding storage of such composite attributes. So this was the part which you already covered. So non-atomic values complicate the storage and encourage redundant repeated storage of data. So example, set of accounts stored with each customer and set of owners stored with each account. So this may give us a redundant data. Next, we assume all relations are in first normal form. So next we have seen about this. Atomicity is actually property of how the elements of domain are used. So here strings will be always treated as a atomic in nature. For example, whatever enclosed in single or double ended comma, that is always treated as a atomic in nature. Similarly, if we take a ID of this kind, we may go for dividing this ID into subparts like department code and personal code, etc. So right now we are not focusing on such values. Right now we are only focusing about multiple values just like name or address, etc. And here we started with the today's lecture, that is a devise a theory for the following. So decide whether a particular relation R is in good form. So that can be decided whenever we are decomposing the relation into subparts R1 to Rn, then that should be a lossless joint decomposition. And that complete theory is based on the dependencies, which is called as a functional dependencies and multi-valued dependencies. So here, each right now we are assuming that relations are in good normal form, that is first normal form. So up to this point, any doubt? Up to this point, any doubt? Okay, let us start with the next point. So here we would like to start with the concept of functional dependency. So in the first normal form, only having the atomic domain, that is sufficient. But whenever we start learning next normal forms, first thing we need to learn is a functional dependency. So here this requires that a value of certain set of attributes determines uniquely the value for another set of attributes. Okay, so this definition seems initially some difficult. Okay, for example, let us go to the previous table, this one. Okay, so here right now I'm having physics and with the building name as Watson. Okay, so building name is Watson. So do you think that whatever the building name is there, this value will change whenever there is a change in the department name? So do you think that the value of building name will change whenever there is a change in the department name? No answer.
Mom,
Yes.
yeah, it's changed because every department have their means different. It's allocated in different places, so it will be
Yes.
changed.
Yes. It means that if consider I take up physics, consider there are five instructors are there into the physics department. Okay, so for this Einstein, I have taken physics. For Einstein, the building name is Watson. So whenever there is a second entry for the physics comes, do you think that the same building name will be there? Whenever we will
No,
refer to
ma'am.
the say we will refer to the another instructor from the physics department, whether building name will change or will remain the same.
It will be changed.
It will be changed. Any other answer?
Yeah, ma'am. Because definitely every department have their every particular building. So
So okay, let us start with the explanation. Okay, forget about the department right now. So here I'm having the name of the student and marks of the students. Okay, these two, or let us take an address of the student also. Okay, so these three fields are there: name, address, and marks. So now student A is there who is living at some address, consider Pandharpur. Okay, and having the some marks like 73. Okay, and some another student is there, student B, and who might be living at some another place like consider Solapur. Okay, and the student might be having some marks like 76, etc. So now, do you think that if consider that this age entry, I'm referring to some another relation, whatever the existence of this value is there, this value existence depends on the age. Here, if consider I change the name of the student to C, okay, if I change the name of the student to C, so now whether this value is going to change or I can predict this value that this will be fixed with the Pandharpur only and there will be fixed marks of 67 or any value. If second entry I am making C student, this student might be living, consider that name is my primary key right now. If I say that right now, you can have a unique name only and see, is there a possibility that this new entry will give me Solapur? Is there a possibility?
ma'am, there is a possibility of address redundancy, but yeah, it's possible.
Any other answer? Anybody else would like to comment on this? Okay, my question. Okay, listen to me carefully. Right now, let us take instead of address, I will take a department name. Okay, and I will take this as a marks. Okay, no problem. So my faculty name is SSK. Okay, right now I'm assuming that this is a primary key. That's why no. And right now my department name is CSE. Now there is another value SSK and who is having department as ENTC. Okay.
No, ma'am,
Um,
it's not possible to again the another entry having the SSK.
okay, directly I will move to the first main point. Okay, this is my name and here I'm having address like Pandharpur. Okay, this is considered some another record is there and there is another entry who is living at some another place. So now, do you think that wherever my name will be there, the same address of Pandharpur will be there everywhere? So here thing I wanted to make sure is that uh, the address of the person completely depends on who the person is. Okay, right now I belong to CSA department, I live at Pandharpur. So wherever it means, wherever my name will be there, the same Pandharpur address will be there. It will not happen that somewhere I'm having a record as Pandharpur and somewhere I'm having a record as Solapur. So there is very less possibility that this record may be there. Okay, so it means that here I'm considering that this attribute is A and this attribute is B. So in case, if consider, here we are learning a concept of functional dependency. So if B's value is dependent on A's value, okay, A's value, then we say that B is functionally dependent on A. Okay, this is the definition of functional dependency. If consider B is dependent on A's value and B is, then we say that B is functionally dependent on A. So when we can say that B is dependent on A, if A is changed, then B should also change. Okay, if A is same, then B must be also same. Consider that there are two tuples T1 and T2. Okay, so this may be having its own A and B, that is first attribute, and second attribute, that A and B, B1 are there. And for the T2 also, I'm having attribute A2, that is any value for the attribute A and any value for the attribute B. Then the functional dependency says that T1's A, okay, T1's A if equal to T2's A, then then we can say B is functionally dependent on A if if T1's T1 and is equal to T2's B2. Sorry, I'm confusing you. Okay, there is a value for A and B are the attributes of any relation, and there is a tuple T1 and there is some another tuple T2. Okay, consider that if these two different tuples are there, then if T1's A and T2's attribute A's value is same, then if there is exist this functional dependency, if there is a value of B which is matching with the T2's, sorry, B2's value with the B1. I hope I am making the sense. Please reply yes, those who have understood. Reply yes, those who have understood this. Functional dependency. Okay, at least single reply got. Yes.
Ma'am,
Yes.
can you repeat it? Means I didn't understood anything. Like now I'm confusing.
Okay.
I mean lots of confusion. Like from where it's come, from where it's come.
Okay. We will take our usual example only then. Okay. During typing, I'm listening keys press noise. Did you also could listen that noise? Key press? Okay, fine.
What, ma'am?
मी कीज प्रेस करताना मला आवाज येतो कीजचा. तुम्हाला पण येतोय का?
Yeah, yeah. It's
कीज प्रेस
coming.
करा.
Means, हा आ रही आवाज. Means येत आहे आवाज.
ओके ओके ओके. So okay, here this is our normal schema. Okay. मग आता मला सांगा माझ्या सीईसी डिपार्टमेंटची जी बिल्डिंग आहे दॅट इज लोकेटेड ऑन द सेकंड फ्लोर. ओके. सो समजा मी इथे लिहिलं मेकॅनिकल. मेकॅनिकल मे बी लोकेटेड ऑन द थर्ड फ्लोर. ओके. Okay, and then I will give here as left, right, etc. Consider I will give this as right, and ENTC all left. Okay, these are the values. Now my question is, माझं डिपार्टमेंट नेम जर चेंज झालं, ही व्हॅल्यू चेंज होती का? सध्या आपण फक्त डिपार्टमेंट नेम आणि बिल्डिंग बद्दल बोलतोय. ह्या दोन ज्या कॉलम मध्ये मी जी व्हॅल्यू दिली आहे ती डिपार्टमेंट नेमची एक आहे आणि बिल्डिंगची एक आहे. डिपार्टमेंट नेम, बिल्डिंग नेम, डिपार्टमेंट नेम, बिल्डिंग, डिपार्टमेंट नेम, बिल्डिंग. सो नाव माय क्वेश्चन इज, समजा मी जर हे सीएससी, मेकॅनिकल, ईएनटीसी ही डिपार्टमेंट नेमची जर व्हॅल्यू चेंज केली तर बिल्डिंग नेमची व्हॅल्यू चेंज होती का? ओके, चेंज होणं. ओके. अँड देन इफ कन्सिडर करा की सध्या की वगैरे काही माझा अट्रिब्यूट वगैरे सेट नाहीये आणि मी पुन्हा एकदा एंट्री रिपीट केली सीएससी. सो नाउ डू यू थिंक दॅट हिअर ऑल्सो आय विल हॅव द सेम व्हॅल्यू? हिअर सीएससी ची जर व्हॅल्यू मी रिपीट केली तर बिल्डिंग नेम तीच येणार का वेगळी येणार? Yes, it means it will change or same. Okay, same. So it means that माझी बिल्डिंग कुठं आहे ते कशावर डिपेंड आहे की माझं डिपार्टमेंट कुठलं आहे. इट मीन्स दॅट समजा हे माझं झालं टप्पल. ओके. हे माझं टप्पल T1 हिअर. This is my tuple T2. Okay. And this one is my attribute A. And this one is my attribute B. Okay. This one is A attribute and this one is B attribute. And this relation is my R relation. Okay. R relation. So functional dependency means that if we are taking T1's A, okay, T1 च्या A attribute ची व्हॅल्यू जर T2 च्या A attribute सोबत जर मॅच करत असेल, then we can say that म्हणजे B is functionally dependent on A if this condition already existing, and we can say that B is functionally dependent on A if T1's B is also equivalent to T2's B. Okay. म्हणजे या फील्डचं एक्झिस्टन्स इज डिपेंडेंट ऑन दिस व्हॅल्यू. जर माझा डिपार्टमेंट नेम जर चेंज झाला ही व्हॅल्यू सुद्धा चेंज होणार. जर डिपार्टमेंट नेम जर माझं सेम असेल देन it implies that attribute B's value will be also matching. Okay. Now is it clear?
Yeah, ma'am. Now it's clear.
Okay. And same with the budget. म्हणजे budget, consider that here I am having budget for the CSC as a 10 lakhs. Okay, I will take this as a 10 year. Okay, and if I'm repeating the value, this will again give me as a 10 year. It doesn't happen that म्हणजे CS is a department इथं 10 lakh and CS is a department इथं माझं 8 lakh आहे. No. Here, this value is an attribute or asset of a CSE department. ही value माझ्या department name वर dependent आहे. Yes, it might happen that some other department is also having a 10 lakh budget. बट दॅट इज नॉट अ ट्रू दॅट म्हणजे असं नाहीये की या दोघांचं 10 लाख आहे म्हणजे या दोघांचं डिपार्टमेंट नेम पण सेम आहे. नो, हिअर इफ डिपार्टमेंट नेम इज सेम, then I can say that T2's A and T1's A is matching, then T1's B and T2's B will be also matching. Then we say that B is functionally dependent on A, and this is denoted by A implied by B. Okay, this is how the functional dependency is shown. म्हणजे B ची व्हॅल्यू ही A वर डिपेंडेंट आहे. ओके, आय होप नाव इट्स क्लिअर. Okay, now let us move to the previous example. Okay, for this purpose, let us take an example of a inspector. Okay, okay, forget about this. We will, as we go with the next concepts, we will go for the examples. So now here, let us read the definition once more. Require that the value of certain set of attributes. Right now here, our set of attributes building and budget determines uniquely, sorry, here certain set of attributes, this is a department name, determines uniquely the value for some another set of attributes. So here certain set of attributes म्हणजे माझं डिपार्टमेंट नेम डिटरमाइन करतं की माझ्या कुठल्या ह्याची व्हॅल्यू म्हणजे बिल्डिंगची आणि याची व्हॅल्यू काय असणार आहे. ओके, सो हिअर इट इज मिनिंग दॅट समजा मी T2चा अट्रिब्यूट बी जर फाइंड आउट करायचं म्हणलं तर मला काय मल्टिपल व्हॅल्यू येणार नाही. म्हणजे असं नाही की मी सीएससी ची बिल्डिंग जर विचारली, ओके, सीएससी ची बिल्डिंग मला फक्त कम्प्लीट टेबल मधून एकच व्हॅल्यू मिळणार, मल्टिपल व्हॅल्यू मिळणार नाही. सो देन आय कॅन से दॅट फक्त इथे एकच व्हॅल्यू येणार. हा, समजा आता माझा टेबल कसा आहे की नको मी आता कन्फ्युजन नाही करत. Let us see that later on. Okay, so here let us see the functional mathematically. Let R be a relation schema. Relation schema, R is my complete relation. So alpha is a set of attributes and beta is also set of attributes. So R contains all the attribute of my schema. In this case, if our department relation is there, then these three attributes forms my R. This can be alpha, this can be beta or anything. Okay, so here alpha is a subset of R and beta is also subset of R. The functional dependency alpha gives beta holds on R if and only if for all legal relations of R it means my relation name and R is a set of all attributes. Whenever any two tuples T1 and T2 of R agree on the attribute alpha, they also agree on attributes beta. That is, if T1's alpha and T2's alpha is matching, then T1's beta and T2's beta is also matching. So here is an example. So this is a doesn't hold a functional dependency. So first you read the definition. I will give a minute, and then we will move to the example. Okay, read this definition. So here, let us consider this is my A attribute, that 1, 1, 3. This is my A attribute and this is my B attribute. But if we take A's value for two tuples, this doesn't give us B's value same for the two tuples. That's why here we cannot say that A holds B or B is functionally dependent on A. But reverse we can say. So reverse here 4 gives me a single value, 5 gives me a single value, and 7 also gives me a single value. That's why reverse can hold here. So now we will talk about some relations. So here key K is a super key for relation R if and only if K on K complete relation is dependent. Okay. So here a super key K is there. K is a candidate key for R if and only if K gives R and for no alpha. So let us read the first definition. K is a super key for relational schema R if and only if K holds on R. So here we are applying some rules of some identity, just like you might have studied those rules in set theory, etc. Identity rule, that is multiplied by something or addition by something gives us the same number. Similarly, here also such rules are applied. So here the basic rule is that if I am talking about A is always functionally dependent on A. Okay, this is a identity functional dependency, so which is what implied. So if consider we are having a k attribute which is a key attribute, and on k complete R is dependent. Okay, so right now we are having department name. Okay, on the department name we are having dependency of the building name, that is building, and budget. These two attributes are dependent on the department name, and department name itself will be also dependent on the department name. So now R, it means that R is a set of complete attributes of the relation. So R will be equal to here. R will be a set of all attributes in that relation. Okay. So now, do you think that this and this is same? These two are same. This dependency and this set is same. Yes, we can say, because these are the all set elements. So reverse of the order of the elements doesn't matter. So I will say department name is a super key on which there are all attributes are dependent. Okay. So K, we can say that this is a super key. On super key, always R is dependent. Okay. So this is the first rule we should always remember. So here we were talking about K is a super key for a relational schema R if and only if on K complete R relation is dependent. Yes, here that's why we have seen a department name, and on department name the other all attributes are dependent. That's why we can prove this that department name is a super key. K is a candidate key. Second rule, candidate key for relation R if and only if K gives R. The first is also true. And for no alpha, which is a subset of K, alpha gives R. Okay. So here, uh, before moving to the second rule, let us focus on the first rule. Okay, so super key, it means that any proper superset of this is also a super key. It means that along with the department name, if I take here a building name, this is also valid. Again, other than this, instead of building, if I take a budget, this is also valid. And this is also valid because on these all attributes, these attributes might be dependent. This is a R. So on department name, already building is dependent. So department name and building budget, I can write here as it is. That's why here we may say that these are the super keys on which the R is dependent. Yes. And here it is said that K can be a candidate key. K can be a candidate key. Right now, this is my K. So here K can be candidate key. This means that right now K gives R, that is true, that K gives R. If I take this set or this set, this will give me a complete R relation. And second rule is that here for no alpha which belongs to or a subset of K, okay, the subset of K we are talking about. Let us take alpha to be department name. Okay, right now alpha is my department name. Alpha is my department name. Or let us take budget to be alpha. Budget is my alpha. Whether budget can give me complete relation, budget can give me budget. And building name at all doesn't depend on the budget. And that's why here the second condition is false. Okay, second condition is false. It means alpha independently budget cannot give me the R. But if I take alpha to be a department name, okay, alpha the proper any subset of K, this is my subset of K. K can be either this one or K can be either these three or K can be either these two also. So department name can give me budget, department name can give me building, and department name can give me department name also. So it means here from this, if I take simply this one, this can also give me. So this is nothing but my alpha. So if alpha gives R, then we can say that K is a super key, and hence here this alpha gives us the complete R, and that's why here this can be only a dependency where this is giving me a complete relation R. So in the department name further I cannot divide. That's why this will be called as a candidate key, but this will be called as a super key only because subset can give me the complete relation. Here this alpha doesn't give me the relation, but this alpha gives me a complete relation. That's why this is a super key. This is also a super key. This is also a super key, and this will be my candidate key. Getting heavy. Okay. Shall we move to the next topic now? So, read this definition once for the super key and candidate key. Okay, here on the department name, salary cannot be dependent because in the department there can be multiple instructors, and for the single department, salary will be having multiple values, and that's why we cannot show this dependency that this dependency should also hold. No. So let us move to the next topic: use of functional dependencies. Okay, so where we can use this functional dependencies. So first, we can use the functional dependencies to check whether relation is legal or not. So let us see what is mean by a legal relation. So we use functional dependencies to test relations to see if they are legal under a given set of functional dependencies. If a relation R is legal under a set of functional dependencies, we say that R satisfies F. So here, the first thing comes when we can say that the relation is legal or not. So legal relation, it means that here whenever we are saying that any of the key attribute, remaining elements or remaining attributes should be dependent on the key element only. Okay, and such relations only will be called as a legal relations. Okay, so legal relations are those relations which are in which or the remaining attributes are always dependent on the primary key. So legal relations, first thing, the all elements should be or all attributes should be in atomic domain. So if relation is legal under a set of functional dependencies, we say that R satisfies F. And next uses specify constraints on the set of legal relations. So legal relations, we say that F holds on R if all legal relations on R satisfy the set of functional dependencies F. So here legal relation, atomic domains and dependency on the key element, that is the rule. And here in a database we will simply check if we are talking about relation R, remaining attributes of R should be dependent on the key element. That is the only way to specify way we can say a legal relation. And if this is holding for all the relations in the database, then we can say that we are specifying the legal database or legal relations. A specific instance of a relational schema may satisfy a functional dependency even if the functional dependency does not hold on all legal instances. So here, this might happen that so whenever we are talking about any relation, uh, just like here on the name id is dependent, so this may not hold true because there can be multiple instructors with the same name. So in that case we may not say that this is dependent on the id, but we may say that if there are two persons with the same name, then name cannot be dependent on the id. But here logically we cannot say that name, if even though two persons are having the same name, id is another additional attribute of a person. Okay, with respect to the database we may say that we are losing the legal instance. So let us continue. Where is the second normal form? Okay, I couldn't find out the second normal form. Yes. So here, a relation is to be said in second normal form if and only if it is already in first normal form and each and every attribute fully dependent on the primary key of the relation. Okay, so this is the definition of the second normal form. The first relation. Okay, so let us talk about the schema. This schema I was talking about. Okay, second normal form. So here we are having a relation with this schema. Okay, right now the schema of relation is ID, name, salary, department name, building, and budget. So now, right now, as ID is unique, so we will take ID as a primary key. Okay, so right now, my schema is of structure of this. ID of the instructor, name of the instructor, salary of the instructor, and department name, building, and budget. These three attributes are there. So now here, my question is that here there are dependencies like uh, it means in which department the instructor is there. So that's why I may say this that on ID department name is dependent. Okay, it means if I belong to the Kadam SS, then wherever I will go, I will have a department with the CSE only. So now, building. Okay, on which attribute this might be dependent. Right now, my ID is a primary key. So, do you think that this ID, that building name might be dependent on the ID? So now, do you think that on the building name, on the ID, building name is dependent, or whether building is dependent on the department name? On which attribute building name is dependent? No answer. So here,
Ma'am,
as my ID changes, yes.
ma'am, I think so. Building attribute is depend on department name.
Yes. Here, thing is that yes, with the different IDs, my building name will also change. But here, the main thing is that this will remain same whenever I'm having the department name same for multiple tuples. I will also have building name same for those tuples also. It means building name is completely dependent on the department name. And that's why here, even here in the this schema, I am having ID as a primary key. Here, this building is completely dependent on the department name. So the second normal form says that here the first thing is that it should be in the first normal form. Yes, I'm having the relation into the first normal form. ID name, salary, department name, building, and budget cannot be divided into subparts. And each and every attribute fully dependent on the primary key of the relation. So here, when we talk about the building name won't change whenever my ID will change. Here, this will change whenever my department name is going to change. So for this department, even though the value is getting repeated, at the same point, building name will also go on repeating. It means that here building name is not dependent on the ID, but this is dependent on the department name. So it means that whatever this relation is there, this is not in the second normal form. This is only in the first normal form only. Okay, and that's why here we take those attributes which are dependent on attribute or other than the key attribute, and we divide this relation into multiple relations. For example, name is also dependent on the ID. Salary, that is what is the salary of individual, that is also dependent on the uh, every instructor, and in which department the student is or a faculty is working, that also dependent on the ID of the instructor. But the remaining attribute, building and budget, these are not dependent on the ID, and that's why here these two attributes need to be removed. And hence, in order to, as these are dependent on the department name, so here whatever department name is there, that should be also combined with those fields. Okay, and hence what are remaining attributes are there, that will be taken into one relation, and remaining attributes will be taken into relation. And hence we can say that after dividing the department into instructor and department, these two relations are in second normal form. Here, clear. So here, this is how we are dividing the relations. So regarding decomposition or dividing the relation into multiple parts, that we can see later also. But right now the thing is that we should learn about how the dependency works. So here, if I say that name, salary, these are dependent on the ID. We These are the individual properties, so we can say that yes, these are dependent on the ID. But when it comes to the building and budget, these two values are not dependent on the ID of the instructor. Here, these two values are dependent on the department name, and that's why in order to make this relation into second normal form, we take out those attributes which are not dependent on the primary key. Okay, on the primary key these four attributes are dependent, so we keep into that as a one relation, and remaining two attributes we will take into some another relation. But here taking these two attributes as independently, that doesn't make sense. Only simply building and budget name I'm not going to store anywhere, because these attributes are having their value from the department name, and that's why here department name, building and budget we will take into some another relation, and remaining attributes into some another relation, and this will be the primary key of the relation, and here this can be a primary key of the relation. Now here also these two attributes are dependent on this, and here also these remaining attributes are dependent on this, and because of which we may say that these two relations are in second normal form. Okay, so now let us move to the next use of functional dependency over. So now let us so whatever this dependency is there, this is also called as a partial key dependency. So if a table has some attributes which is not dependent on the primary key of that relation, then it is not in a two nor second normal form. So here we are talking about that second normal form, no partial key dependency. Okay, so no partial key dependency, only key dependency should be there. If we are having any other attributes dependent on some another attributes, then we can say that that is a partial key dependency here. Okay, so clear with this? So no partial key dependency is allowed in the second normal form. So then let's move towards this. Then the next concept, trivial dependencies. A functional dependency is trivial if it is satisfied by all the instances of a relation. For example, trivial, the same department name dependent on the department name. It is in the same format. Example, ID and name. On these two attributes, ID is dependent. Yes. On the name is dependent, or name holds name. Then we can say that this is also trivial functional dependency. In general, if alpha gives beta, it's trivial if beta is a subset or equivalent to the alpha. Read a definition for a minute. Closure of a set of functional dependencies. Closure, it means that there is some functional dependency given to us, and from that can we derive some other functional dependencies. Okay, so this calculating the closure, that is the same property. So given a set f of functional dependencies, there is a certain other functional dependencies that are logically implied by f. Okay, so for example, if we say a equal to b and b equal to c, then it implies that a is equal to c. Okay, in the same way we apply to the functional dependencies. So for example, uh, a holds on b, or b is dependent on a, and b holds c, then we can infer that a holds c. Okay, so this rule is that B attribute is dependent on A. C attribute is dependent on B. So indirectly we can say that C attribute is also dependent on A. Okay. So this is a implied functional dependency. So here, and this is only single rule. There are some rules are there. If we apply those rules and calculate a set of complete functional dependency, then that set is called as a closure of F. Okay, F, it means that this is a set of functional dependency, set of functional dependencies F, and within the F we apply some rules, and that is logically implied rules, and then whatever the complete subset is there or superset is there, that we call as a closure of a F. Okay, so we denote the closure of F by F plus, and F plus is a superset of F. So here, closure of EF, it means that the set of all functional dependencies logically implied by F is the closure of EF. Okay, so read this definition for a minute, then we will go for the next example. This is a superset. This is always given by uh, F plus. Okay, let us consider this is my example. Okay. On the roll number, name and marks are dependent, and on the name, marks are dependent. Okay. So here, let us take assume that we are having a relation R or a student relation. Okay. Uh, Within the student relation, uh, we are having roll number, okay, then name of the student, and then marks of the students, and location of the students. So these are the attributes of a student relation. And within that, roll number is my primary key. As usual, we will take roll number as unique value. So in that case, whenever we are saying that on the roll number, name is dependent. So we may say that, and on the name, marks are dependent. So here, in order to calculate the closure of a functional dependency. So let us see what is meant by functional dependency. Functional dependency is a set which is a collection of all the functional dependencies on a relation. So whatever these two functional dependencies we are having, so this combinedly will form my F. Okay, this is one functional dependency. So here I will make this as a comma, or I will make this as a separate as a semicolon. So in short, these attributes are not separated by the comma, where we are having name, marks, etc. That's why we are separating by comma. Usually, whenever explanation is carried out in terms of A, B, C, D, etc., the explanation is given, and then we don't use comma. So attribute on A, B, and C are dependent. So we may say A holds B, C. So okay. So this is how we are giving this functional dependency, and another functional dependency will be given like this. So, okay, this is how, or we may say that these are the two functional dependencies, and these two forms our F. So we are calculating F closure. So F closure is given by this structure, F plus equal to. So whatever existing functional dependencies are there, these will be also a part of this functional dependency. So we will copy these two. So here there are actually three rules which are applied on this. So first one is a union rule. First is union rule, then transitivity, and last one is a pseudo transitivity, or we may say that adding the attribute to the left or right side. So these rules are called as Armstrong axioms. So which says that, and here distribution rule is also there. So okay, these are the three rules which are getting applied. So if consider the union rule says that if consider we are having two functional dependencies, we can combine these two, that is left side with the left side and right side with the right side. And whatever those attributes are multiples are there, that we will remove. So it means that if we apply the union rule, roll number and name. Okay, so here I will separate by the comma. This both can give me the name of a student, marks of the students, then and location. Okay, so whatever name is there, that will be getting repeated, and name is also there on the right side, and that's why we will not take on to the left side. Okay, so this is how the functional dependency is given. So union rule, combine union, performing the union of left sides and combining the union on right side. So any doubt in the union rule? Next, transitivity rule. So on the roll number, name and marks are dependent, and on the name, marks are dependent. So actually, it implies here that on the roll number, marks are dependent. So we will not take that. Yes, we can take here. On the roll number, name is dependent. On the name, location is dependent. So we can add the rule as roll number holds location. Okay. So this rule will be implied by this. Roll number gives names, name gives location. So in this way, we can say that here the rule is transitivity rule got applied. Am I audible to all clearly? Am I audible to all clearly? Okay. So next comes distribution rule. Distribution rule says that whatever the remaining parts are there, that is on the right side, that we can distribute. It means on roll number name is dependent and on the roll number marks are dependent. So this will add two rules, and on the name marks are dependent and on the name location is dependent. So this will add again a rule. Okay. So if we are able to do this, then that rule is also added. So these are the three rules. Let us see those rules in detail in the next lecture. So today we will stop here. So if you are having any doubts, you can ask the queries.